Hello, I welcome you all to this another interesting screencast. And the problem reads: draw the shear and moment diagrams for the compound supported beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So to start with, we are going to draw the free body diagram, and since this is a compound supported beam, we are going to dismantle a CD, draw a free body diagram separately, and ABC. So there we go. So we have two beams. We have one like this, then we have another one like this. Okay. Okay. So we have distributed loading up to there, right? Like so. And this has the intensity of 3 kilonewtons per meter. This point is A, then we have B, then finally we have C, which is a hinge. At A we have a hinge. At C it is a pin. At A we have a hinge, so expect AY and AX. At B we have a roller, so just expect a BY. And then we have C there, we have D. Okay, we have a 5 kilonewtons, and the span, the length for this is as follows. Alright, I think I'll put them at the bottom. This is 3 meters, this is 3 meters, and then we have this is 1.5 and this is 1.5. We expect a reaction at C. I wanted to start with member CD because this is where I'm going to start my calculation, but it doesn't really matter where you start from. Okay, and then we have a dollar there, dy. Right, so let me apply the equations of equilibrium quickly on CD, and then I'll move to ABC. We're going to have an equivalent force here that will just be acting directly on the support B, and this is going to be equal to 3 times 6, which is equal to 18 kilonewtons, and is acting at the location 3 meters. Right, so summation of moments about point C equal to 0 and clockwise being our reference. We already know the solution there, right? This is simply supported with concentrated at the midspan. So we know Cy and dy are going to be the same, 2.5, but we just need to calculate, right? So we have a minus 5 by 1.5. Of course, Cy and dy, like I said, are going to be equal, and they will be equal to 2.5. So 5 by 1.5 plus dy by 3 equal to 0. Therefore, our dy, we know if we did our calculations, is going to be equal to 2.5 kilonewtons. Summation of forces in the y equal to 0. Alright, so we have Cy plus Ty minus 5 equal to 0. We've already calculated what dy is. Dy is 2.5. Therefore, our Cy, if we did the calculations there, it gives us a 2.5 kilonewtons. Summation of forces in the x direction, there we know that our Cx is equal to 0. So we are done with this part. Move on to the other part. So we know that Cy is equal to 2.5. And so is this Cy 2.5, dy 2.5. And Cx is equal to 0. So with that information here, we can take moments about point A. Summation of moments about point A equal to 0. Right. We also know here that what do we know? Okay. Let's go ahead. So we have minus 18 by 3. Um, then we have by by 3. Then we have minus 2.5, which is cy by 6, equal to 0. Therefore, our by is going to be equal to, what do we have here? Minus 18 by 3 minus 2.5 by 6, and then divided by 3. So this is going to be equal to 23. Let me repeat it. 18 by 3 minus 2.5 by 6, okay, divided by 3, 23. Okay, then we have summation of forces in the y, like so. What do we have? We have ay plus by minus cy, which is 2.5, minus 18 equal to 0. We've already found what by is. Therefore, our ay is just going to be equal to 23 minus 2.5 minus 18. So ay is just going to be equal to minus 2.5 kilonewtons. So it will be in the other direction. So 23 minus 2.5 minus 18. Okay. Right. So I guess we are done. This is 2.5 minus. I mean, this has to just change. This changes like so. And then by is 23. Right. And this is what we expect for sure. So what do we have? So we just need to now get rid of this so that we have some space. Okay, so with this information now we can quickly start now doing the we can now do the plots without drawing anything. Of course, we didn't calculate x. The summation of forces in the x direction is going to be 0, you know that, right? Because we don't have any loading in that direction. Ax will be equal to 0. So this is equal to 0. So quickly, let's draw our lines for shear, preparation for shear and moment. Okay, there we go. So this is shear force diagram and this is bending moment diagram. This is 0, positive up, negative down. This is positive up, negative down. Right. So what we are going to do now is we start doing the plots. So we have at ay we have a negative 2.5. So let's just indicate it. There it is. So this is 2.5 kilonewtons. All right. So then later on we have a distributed loading from A to B of 3 kilonewtons. So the load is negative and is constant. Therefore, we expect the slope for shear to also be negative constant, to have a negative constant. So from minus 2.5, we need to be mindful this value is minus. So we are going to again subtract it, so these are going to be adding since they have got the same sign, minus 3 times, because also the distributed force is negative, 3 times 3 in that interval. So what does this give us? Negative 2.5 minus 3 by 3. Of course, this gives us a negative 11.5. So let's say we have 11 somewhere there, or somewhere there, right? Okay, sorry, somewhere there. That's our 11. Let's connect those lines. So for sure, this is negative. This is a negative slope. It's negative with a constant slope. Okay, negative constant slope. So this value here is 11.5 kilonewtons. Then at B, alright, this one I think I have not indicated it where exactly I supposed to be. Let me just demarcate these lines so it's easier for me to locate this. Alright, so we said 11 is here, okay, and it has this value is 11.5 kilonewtons. Okay, then at B, immediately at B, we have a counter shear force, which is positive, which is going to further increase this from minus 11 to a value that will be positive. So minus 11.5 plus, because it's positive, plus 23, this gives us plus 23, it gives us 11.5. So this value will be increased to a point 11.5 in the positive region. Right. So there we go. So we have 11.5 kilonewtons. Then from B to C, our load again is negative constant. Therefore, the slope for shear will also have a negative constant. So let's see what this value is going to be. So we have a positive 11.5 minus 3 times 3. What does this give us? Gives us a 2.5. So let's say it's going to come up to somewhere there. Okay, something like this. Then finally we have a shear, which is going to further reduce this moment. So this value here is 2.5. Okay, so we still have at cy, which is negative. So therefore, if we did an algebraic addition, 2.5 minus 2.5 is equal to 0. Therefore, this closes at this point, and this is what we expect. If it fails to close, then something is wrong. You need to get back to check. So this is positive and this is negative. So we are done for this one. Let's go to the next one. The next one, we have positive 5 going up. Positive 5, so let's say up to there. Okay, so this is our 5. Alright, going up by 5. And then from C to the point load 5, this interval, our load there is equal to 0. Therefore, the slope for shear is also going to have a 0 value. It is just going to be a straight line, straight horizontal line with 0 slope. And then immediately it reaches the point where we have 5. we are going to have a change of behavior there. So we have a 2.5, we have a 2.5, then minus 5, which gives us a negative 2.5. So we're going to have a drop from this point down by 2.5 up to there, right? So this point is also 2.5. Then from the point load to D, again, we have a load of 0, therefore slope also will have a 0 slope. So we expect this to just be again a horizontal line like so. And then at dy, we have this value of 2.5. So we have negative 2.5 plus 2.5, which again is supposed to do what? To close. Okay. So you expect a closure. Great. So this is also 2.5 kilonewtons. This is negative, this is positive. So we are done with this one. Okay. Let's go to the next one for moment now. Bending moment. All right. Of course, this is also shear force diagram, and so this is bending moment diagram. So we use the same principles. When we look at the shear here, the shear is negative and is increasing. Therefore, the slope for moment will also be negative and increasing, right? That's what we expect. So it will be negative. So which of the graph gives us negative and increasing? Between this one and this one, which one gives us an increase between the red and the green? Negative slope. Of course, both of them have negative slope, but which of the two will have an increasing negative slope between green and red? Of course, it is the green one, right? You agree? Yes. Okay. So it's a green one. So, and we also know that at the support A, which is a hinge, we don't expect any moment unless we had an externally applied load, or if we had a fixed support, but we have a hinge. A hinge does not transfer A moments, it only transfers horizontal and vertical translational forces. So here, and since the shear is governed by a polynomial of degree 1, we expect the moment to be governed by a polynomial of degree 2, which is a quadratic function. And we also established how it's going to open. It's going to open like so. Okay? Negative increasing slope. Okay, let's say it comes up to there, something like that. All right. So let's say this is the value. All right. And then from B to C, we have shear that is positive and decreasing, right? Therefore, the slope for moment is going to be positive, but also decreasing. So we know the shape already, right? So we expect a replica, something like this. All right. So this is a negative moment. So we expect a zero moment at both the A and C because we have pin connections, and pins do not transfer moments unless we had an external applied moment at that particular point. Okay. All right. So we'll need to calculate this value, which we'll come and do later on. Let's move on to the other side. Here at C, we have shear, which is positive and it is constant. We also expect therefore the slope to be positive, to have a positive constant value. Alright, so we know this one is quite direct. It will just rise from there, let it rise up to somewhere there. Okay, calculate this value later on. And then from from the point load to D, we have shear that is negative and constant. Therefore, we expect a slope to be negative, to have a negative constant value. All right, so we expect this to just fall down like so. All right. Of course, at the very ends there, since those are again pins, we don't expect any moment there at C and D. So let's calculate the value for this one. Okay. So how do we calculate that value? Again, we know that the area under the shear diagram gives us the moment. So we can use either this portion, which is similar to that one, right? Let's use the left hand side, which is that's a trapezoid. So the area for that one is going to be equal to 2.5 plus 11.5 times half times the length, which is 3, right? So 2.5 plus 11.5, okay, times half, which is 0.5, and then times the height, which is 3. So this gives us a 21. This value is 21 kilonewton meters. Let's find this one. It's the same thing also that we are going to do. So the area for, we are just going to use this one. The area under the shear diagram gives us the moment. So that one is, let's call it area 2. I mean just area. Area is going to be equal to 2.5 times the length, which is 1.5. This is rectangular. So 2.5 times 1.5. 2.5 times 1.5. This gives us a 3.75. Okay. Let me just remove that. All right. So area is equal to 2.5 times 1.5, and then we find that this is equal to 3.75. Therefore, this one is 3.75 kilonewtons meter, and this moment is positive. We are done, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, and continue sharing my videos. Bye bye, and see you in my next screencast.